Go ahead and continue. So we've looked at timing channels in general, and the cache channel, and then the power channel. Let's look at other the case of electromagnetic radiation. So radio waves. So this is another type of leak that kind of happens accidentally all the time. So computers, all of our electronic devices are every wire and circuit board trace on in all of our devices is a little antenna, right? And it's and these devices are broadcasting over the radio, over the airwaves, just accidentally all the time. And these electromagnetic emissions can be sensed in many ways. Now, there's whole agencies in the U.S. and presumably in Europe and elsewhere that one of the things any consumer electronics device has to go through in order to be sold on the market commercially is to go through an evaluation process just to make sure it's not emitting too much electromagnetic radiation. So this is just one of the standard pieces of pain that hardware manufacturers have to go through. Try building this great new laptop or something, a phone or whatever, send it to the testing labs, they come back, say, sorry, your device is emitting too much radiation in these particular frequency ranges. Go back to the drawing board, add, and you have, go back, change the chassis, add more metal to it, more shielding, more, more this or that to reduce the amount of radiation. So, so it's, long been very well known, kind of on the hardware side that all of this stuff accidentally broadcasts, accidentally broadcasting all the time through the natural electromagnetic emissions that it produces. But as you might guess, these emissions can be used under the right conditions also to say to break cryptographic operations or steal secrets in other ways, right? Once again, so in this particular experiment, this was done against ECDSA, the elliptic curve digital signature algorithm, which uses, in its naive, most convenient to implement form, does something somewhat similar to the RSA square and multiply. This is because for elliptic curves, double and add is more or less what amounts to more or less the complement, the analog of square and add in the integer fields that RSA is using. And so, these double and add operations are much smaller and quicker. So this is a somewhat more, in this case, this was a somewhat more difficult, more advanced attack required more advanced signal processing, but still, it remains very feasible if the code is written in this variable time way that causes noticeably, distinguishably different electromagnetic signatures when it's doing a double versus doing a double and add. Right? Now, in these kinds of situations, I'm actually not sure in this particular experiment or in this case of the last one whether these particular attacks would have been eliminated if this code was if a constant time code implementation would have been used. Probably these particular attacks would have been eliminated, I'm guessing. But that doesn't mean that all, even a fully constant time implementation could still have a power or electromagnetic, could still be vulnerable to power or electromagnetic attacks, because the transistors inside the machine still have to hold the 1s and 0 bits of the secret data, and the way the transistors flip, and the way the electricity flows, depending on whether it's a 0 or 1, could still produce different power or electromagnetic signatures for the 0 or 1 case that could in principle be detectable, especially using advanced techniques like differential power analysis, like I mentioned. Now, that kind of attack is much harder, and I don't know if, I'm actually not sure offhand if someone has demonstrated a power or electromagnetic attack against code that was written to be fully constant time, and it was really kind of extracting the bits literally out of the zeros and ones at transistor level. That sounds pretty hard to me, but but not impossible in principle. So, like I mentioned, the issue of electromagnetic radiation has a long history. Hardware manufacturers have to deal with it all the time. Security agencies like the US NSA has known about it a long time, and has for decades had the capability of remotely reading the contents of a CRT screen, a monitor, from a significant distance, or from through the walls of an unshielded room or something like that, just by reading and properly decoding and analyzing the electromagnetic signatures. And so this was exploited back, like 1943 initially, by the NSA Tempest program. And because of that, it's for decades been standard practice in kind of US and presumably other defense circles to have rules that anywhere government classified or secret, top secret information is stored or used, or anywhere you have meetings with in which devices access this kind of data, tend to have to be Tempest shielded, have to have kind of special coatings on the walls to minimize the amount of electromagnetic radiation that leaks through that could reveal these kinds of secrets. So, so now, kind of the top spy agencies have been doing this for decades, but it's only, it's only more recently been the case that this kind of attack has become democratized or commoditized, so that pretty much anybody can buy or cobble together the right hardware you need to perform this kind of attack. And so people in the hacker and black hat type community have demonstrated these kinds of attacks possible using very cheap commodity hardware and software systems. So like one device attacking a laptop just that it's held near. Right. So in principle, that could be something you're carrying in your back pocket, and I think thank you for your private key there. In principle, if that works. I don't know exactly which crypto systems and stuff that demo was effective against, but anyway. So, and of course, electromagnetics are not the only types of emissions that machines make. So they also make noise, especially the classic PCs tend to have voltage regulators, and those tend to produce audible noise that actually produce whining sounds whose precise frequency and waveform depends on what the machine is doing. And so, so in another example, it was shown that you could, a machine, disconnected, sitting, nearby on the desk, could just listen to the sounds that this other machine was making, or that the PC was making, and recover recover an RSA private key that way. So here's an example of how that analysis works. And basically, if you look down the right, you can see the different types of instructions that and the different waveforms they would produce that you can read off that way. So. Of course, these work differently. You always have to know the exact implementation of what you're attacking to make this work, and it works differently on, for example, different implementations of RSA. Other versions of RSA, instead of use an optimization based on the Chinese remainder theorem. So, for using pre-computation, and so decryption looks different. But even and that makes the kind of the standard easy attack not work anymore. But a different attack still works. So in this case. Your the bit is either related to the part of the mod P or mod Q, and you can basically tell the difference based on where the hotspots are in this pattern. So I don't know all the details, but basically, again, you analyze it the right way, and and the information falls out. Power, electromagnetic emissions, sound emissions, pretty much any kind of emission a computer accidentally makes. It's been shown that that can potentially be an avenue for side channel attacks. Now things get even more interesting if the attacker doesn't just have to sit by passively, but can actually poke and prod the system in different ways. And again, often it's possible in practice for the attackers to do this, right? Let's say a bank ATM machine. That kind of device. It has to live in an extremely problematic attack model, because ATM machines tend to be on the outside of a building, in the open for anyone, especially including a would-be bank robber who wants to steal money. There's the ultimate target for if you just want to steal money and can find a way to attack an ATM machine to get the cash inside. And the machine is by definition exposed, and the attacker can walk up and poke and prod it, and do all kinds of things. And of course, they're built so, hopefully to withstand quite a bit of physical attack. But it's been shown that there's ways to make the device behave in a faulty way by changing the voltage, temperature, other things. So other inputs. If you can't get into the machine itself, but you can muck with the power supply, the cable that's through which it's plugged into the wall, you can get to that and tamper with its voltage supply in such a way that sometimes it's running on too low voltage, or it's getting spikes or things like that. That can inject faults. Cause random bit flips, and these kinds of bit flips can can cause leakage in all sorts of ways. So again, there's been fairly powerful general techniques that have been developed to take advantage of faults. So you might think that, well, if I can just cause random bit flips and I don't even get to control where those bit flips are in memory or in the processor or whatever, how good is that to me? Well, it turns out that it's pretty useful even if you don't control where the bit flips are, because of techniques like this, because of techniques like differential fault analysis. And that's partly, again, because in many realistic situations, the attacker gets many tries. And in this case, the important point is, if this, say, AES or RSA, or the encryption and decryption, the critical loop is run many times using the same private key, sometimes maybe even the same data, or at least related data, the attacker gets many samples. And if the attacker can cause some of those to be faulty, to have a bit flip somewhere, then the attacker can then do a comparison between the faulty and non-faulty ciphertexts that come out, and often use the arithmetic relationships of that. So like if what's supposed to come out is supposed to be a digital signature, for example, well, a faulty digital signature is obviously not going to check out. It's going to be obvious that it's not a correct signature, and it might even be obvious which bit was wrong. Like I can tell this would be a correct signature if I flipped that one bit. It's not necessarily that hard to do that. And because of the arithmetic properties of many of these crypto systems, that once you identify the one bit that got flipped, you can also identify with some precision where in the processing path it got flipped, right? Because if it was back here, then it would have caused this set of bits downstream to get flipped. But if it's here toward the end, then it only flipped 1 or 2 bits in the final output. Things like that. So through this differential analysis, the comparison between faulty outputs and correct outputs, the attacker can learn information about the true secret inputs that went into these calculations. And this again works in a fairly general fashion across multiple different types of algorithms. An even more impressive fault-based attack that's been kind of attracting a significant amount of attention recently is called Rowhammer. Anyone heard of Rowhammer? Yeah. Okay. Yeah. Can you what is Rowhammer? Yeah.
So Rowhammer is an attack on DRAM, which is the kind of my memory that most of people use nowadays, which exploits the fact that memory has been getting smaller and smaller, and due to the fact that it works with capacitors generally, it is possible to flip certain bits of memory by repeatedly flipping rows of memory at the application.
Yep. Yeah. Exactly. So DRAM is a physical device, and it's been it's the manufacturer for competitive reasons. The manufacturers have been getting it getting it as close to the specification maximum, running it as close to the limits as possible. And so bit flips naturally happen once in a while anyway, but if you literally hammer it by exercising a particular row of the RAM deliberately, then you increase the chance of certain bits being accidentally flipped, just because of the unreliability, the natural, imperfect reliability of the hardware. And when you can do that, if you do that in the sufficiently clever way, now of course it's difficult to predict or let alone determine which precise bits you're going to be flipping, right? And that's and so because usually it's pretty random. But if you play it the right way, and I don't know all the details, maybe you know better than I do exactly how they do that. So if you get lucky and flip the right bit, the correct bit, that might be the bit that representing in kernel memory representing the read-write or kernel user bit permission bit on one of your pages. So if you manage to get the kernel's flip the bit in the kernel's page table that was supposed to say your code pages or your data pages are to say the kernel's code and data pages is kernel accessible only, and you flip it so it makes it user accessible, well, suddenly you can go and read and write kernel memory, which is great if you're an attacker, right? So of course you have to get pretty lucky for one of these DRAM attacks to flip one of those specific bits. But in these attacks they use different techniques, again, that I'm not familiar with all the gory details, either to increase the probability of flipping the particular bits you want, or to just make it harmless, arrange so it's relatively, you just try to flip a lot of bits and arrange so that it's relatively harmless all of the times you try and don't succeed in flipping the bit you want. So you cause a harmless fault and you get control back, and then you get to try again. So if you can just arrange it so you don't immediately die when you don't succeed, and then you try millions or billions of times until you do succeed in getting the right bit flipped, then you win, right? And so that's, again, a standard attack method of the attacker. As long as you can arrange to be able to try many times until you guess right and get the right bit flipped to achieve your objective, then you can get pretty spectacular results in these ways. Now, one of the ways Rowhammer, I thought Rowhammer was particularly impressive is after the original Rowhammer attack came out, which is basically an attack demonstrated in a normal process you assume the attacker has control of a user level process, and the attacker wants to get kernel privilege, break into the kernel, or something like that. But later, a variant of the Rowhammer attack was demonstrated from downloaded JavaScript code. So you could just be running your web browser, Chrome or Firefox or whatever, and you get a ordinary untrusted JavaScript code from a random website that you're browsing. That JavaScript code can, in principle, run the Rowhammer attack. Of course, this is pretty CPU intensive. It might, you might wonder at what point, at some point, why this website is making, is driving your CPU time to the roof for seconds and seconds and making the fan whir and all that. So you might get suspicious. It might equally be, trying to mine Bitcoin on your machine. I guess that's another recent attack with those symptoms. But anyway, kind of in principle, a Rowhammer attack could be something you just get on JavaScript from a random website, and these JavaScript virtual machines have because they're fully programmable and they can access memory. It's of course sandbox memory, but they can hammer the DRAM rows just like user space native code can, and so you can, in principle, a successful Rowhammer attack doesn't even need to break out of the JavaScript sandbox into the browser. It just skips straight from the JavaScript sandbox to the kernel, and which makes it particularly powerful if it's effective. Now, I'm not sure actually the level and types of defenses that have been deployed to guard against these kinds of attacks. I understand, there's been some activity in that area, but as far as I know, it's fairly ad hoc. So other side channels. So we talked about other types of emissions. You can have optical covert channels. So there was an interesting demonstration about ways to use. So if you in many secure environments. So we talked about mandatory access control in an earlier lecture in kind of secure, high security environments with mandatory access control where all classified information is supposed to stay in this room and nobody's supposed to be able to leave without it. Even those who have access to the information aren't allowed to leave without it or email it or anything like that. Well, what if something in that room, some device in that room is compromised, somebody brings a compromised device in, and all it can do is blink an LED, so in this particular attack it was, they used the LED on a disk drive or something like that. And so all it does is, kind of take secret data and then, blink it, turn it into basically Morse code, blink it out through this LED. And of course, it's not a very bright LED, but if, that's the only thing that's blinking, or if the other sources of light can be filtered out, analyzed out, or whatnot, then a camera just pointed at the room's one window from fairly far away can be used to decode that signal, even if it's very subtle. And so that's that's yet another avenue for attack. In conclusion, in general, there's many of these types of attack channels. For some types of attacks, we're farther along than others in terms of finding general defenses, approaches to defenses. Probably the most one of them being writing constant time code, which is becoming more and more common. But of course that's reasonably effective at guarding against timing attacks against cryptographic code. But of course you notice I focused mostly on cryptographic code. Well, why did I do that? Well, because cryptographic secrets tend to be the easiest attack targets, where a successful attack can exfiltrate a small amount of information and get a really big bang for the buck, right? So with cryptographic secrets, and that's basically the purpose of cryptographic secrets, right? To have a small secret key that, as long as you can keep it secret, that keeps this, this big blob of, gigabytes blob of encrypted data private, right? But if you can extract the small secret key through side channel attacks, then you automatically break the privacy of this big multi-gigabyte blob of data, right? That doesn't mean that cryptographic algorithms and code is the only potential target for side channel attacks. So potentially any code that deals with sensitive data and that does branches on sensitive data or processes sensitive data could also be a target for side channel attack. And it's not clear how practical it is to go through all of our code and rewrite all of our normal processing code to be side channel resistant as well. And so that's a big open problem, and it only deals with the timing channel attacks. So there's the power, visual, acoustic, type attacks, and while the constant time defenses and some of the defenses that apply to timing channels can help defend against these other attacks as well, they aren't complete solutions either. And so I don't know, developing really complete systematic solutions, as far as I know, is still a very much open problem. So, yeah. So, any further questions? So this will. Okay. Yeah. So I'll stop early this time, and yeah. So that's all. That's all for today. Thanks. See you. Oh, and next week, my group member Linus Gasser will lecture in place of me because I have to be away. So I'll see you in 2 weeks, but come back next weekend.